So to start out the 3D coordinate system, I'm just going to compare it to our old 2D coordinate system that we know so much about. So we know that in the 2D coordinate system we have ordered pairs. We have x comma y that we graph on an x and a y axis. But when we move to 3D, obviously we're going to need 3 coordinates. We call those ordered triples. And we call them x, y, and z just to add that height element. And like I already told you, this x-axis is the one that sort of comes out of the paper at you. And then we put the y-axis horizontal and the z-axis goes up and down. In 2D, our distance formula basically used a Pythagorean theorem. It found the distance between the x-coordinates and the distance between the y-coordinates, and then we could use a Pythagorean theorem to find the distance between 2 points. And this time we're still finding the distance between 2 points, because that's still how 3D space works. The only difference is our 2 points are actually ordered triples. We could go through why and how this works, but it actually works just like you would want to have it work, how you'd expect it to work. Just adds that one more term where we find the distance between the z-coordinates and include it in sort of an extended Pythagorean theorem. It's actually a few Pythagorean theorems kind of combined together. The midpoint formula, if you have 2 points on a graph, there's a point that's right in the middle. To find that point, you're going to average the x values and average the y values. In a 3D coordinate system, if you think of just 2 balloons floating in the air, there's still a halfway point. So you can still find a midpoint between 2 ordered triples in space. And yes, it does work just like you'd hope. Again, that's just the average of the x, y, and z coordinates. And the last thing I wanted to compare was the equation for a circle. This is the format that we learned it back in, I think it was chapter 1. We had that sort of ellipse form of the circle too, where we had it equal to 1. But that's basically the equation for a circle. The equation for a sphere. Again, that Pythagorean theorem still kind of works in 3D. I'm pretty sure I think they use J for that third coordinate. And it's still r squared, because we're still talking Pythagorean theorem, so it's not r cubed, it is still r squared. We'll talk about that more tomorrow. For today, I just want to kind of get you used to graphing on the coordinate. It's not coordinate plane anymore, it's more like coordinate space, right? So we actually have 3 planes in coordinate space. The xy plane, and if you think about when we drew our little model room, the xy plane is the floor. So if we shaded that all in, I might start that over. If we shaded in the floor is the xy plane. When you think about the yz plane, well, that's where the y-axis and the z-axis form together. So that's really like that front wall of our classroom. It's technically going to go outside of our classroom too, because planes are infinite, but it's the, I guess, sort of vertical surface that's flat against our front wall. The xz plane, also a vertical surface, only it's the other wall, the wall that has the door on it, if we're trying to picture it in this classroom. So before we were only talking about this part of that plane being the wall inside our room, but that same wall extends into Mrs. Brock's room and down into the basement and everything. So that would still be considered part of the XZ plane. It's a little challenging to plot points, but that's why we practiced some drawing originally. So we're going to try to plot the point X, Y, Z, 4, 5, 3. Remember, positive X comes out of the board, positive Y goes to the right, and positive Z goes up. So when we plot 4, 5, 3, here's what I'm looking for. So we're going to come out on our ticks and we're going to go 1, 2, 3, 4. This is the point right here where X equals 4. And then since this is a positive 5, that just means that we're going to go to the right by 5. Now we're going to go from right here. So we're going to go 1, 2, 3, 4, 5. So we've come out 4, we've gone over 5, and now we need to go up 3. And you notice that we don't really have like a vertical axis, so you kind of just have to imagine that you had your z-axis sort of ticked out. And what we're looking for is a height that would be equal to that would be equal to 3. And so I'm just going to do my best to copy that. And so from that point, I need to go up in the air. So I've come forward, I've gone to the right, and now I've gone up into the air. And if you can picture that, that point is sort of floating there in space. For me, I can picture that. For you, if you want to give any extra lines in there, you could draw this line out. If you wanted to go up 3 and draw this line out. Really what you have is you have the corner of a box going on here. To me, it's good enough just to draw that pink part, but I guess I can see that better, that this point right here is kind of that upper corner of that box coming out. It's just up to you. If you can see it well enough, see that it's coming forward to the right and up from there, that's good enough for me too. So let's try just a couple more. This one's 4, 5, negative 3, just to see the difference. So we're going to come out to 4. We're going to go positive 5 in the y direction. And this time, instead of going up those 3 units, we're going to go below the floor, down 3 units. Again, this is my 3 units that I would have copied from my z-axis. How's that one? If that one's hard to see, I don't know, maybe it would help since we're going down into the basement if we made that a dotted line, just to show that, you know, we're going down into where you can't really see. Something like that. Something so that you can just get a sense for where those points wind up. Alright, the next one, negative 3, 5, 4. So this time, instead of coming out of the board towards the positive x, the negative 3 just means we're going to count back into the wall. It's almost like we were going back into Mrs. Brock's wall. The 5 is our y value, so there we are, 5 units into her room. And then back in her room we are 4 units up from there. Maybe another way, if you wanted to, you could label each distance. That's 3. This is 5, and then that's up 4. Maybe you even want to put the negative 3, so you can just say that you were going backwards. I think that's a pretty good job of showing where that point is hanging in space. Last one, we're going to go backwards 3. This means we're going to go to the left 5, and then up 4. And I would like you to be able to picture where that would be. Like, which of those 8 boxes does that wind up in? It's not the first one, it's not the second one, that was Mrs. Brock's room. It should be in the 3rd box that we talked about before. And let's just talk about those boxes one more time. When we were in my room, we already talked about how that was the x was positive, the y was positive, and the z was positive, right? When we go into Mrs. Brock's room, what changes? We're still Oh no, we're not coming out in front, we're going behind. So that would be an X value. So back in Mrs. Brock's room, we're actually going backwards. So then we have our X is negative. We're still going to the right, so Y would still be positive, and it's still upstairs, so Z is positive. Now when we talk about these 8 boxes, it actually is a little bit comparable. I skipped over this at the beginning, but it's comparable to the octants versus the quadrants. So you know how the quadrants are labeled? The quadrants are labeled 1, 2, 3, 4. Well, since there is 8, we don't call them octants anymore. We call them, we don't call them quadrants, we call them octants since there's 8. So it's kind of like on the top floor we've got 1, 2, 3, 4. But then we have those basement ones too. So underneath 1 we've got 5, 6 is underneath 2, 7, and 8. So that would be where the Z values are negative, right? Would be our downstairs. That's where you're going to find octants 5, 6, 7, and 8. Just to see if we've got this, let's go back to our points again and just see if we can figure out what octant each of these is in. Remember, if everything's positive, that's octant 1. Now this one, 2 of our things were positive, but then we went to the downstairs, right? So that would be 1, 2, 3, 4 is top floor. So 5, 6, 7, 8. 5 would be right below the first octant. This one's a Mrs. Brock's room, right? Because we're going backwards into that wall, but then we're staying to the right and we're staying top floor. So this is Mrs. Brock's room in octant 2. And where is this if you think about rooms? Okay, so it's back and to the left upstairs. So it's back out into the hallway upstairs. So since it's an upstairs, it's going to be a 1, 2, 3, 4. So we start 1, 2. This is octant 3 over here. Now I know I'm skipping around a little bit, but now that we're kind of thinking more in the octant sort of idea, I just want to talk to you about what do we know about every point that's on the floor. Well, every point on the floor has no height. So every point on the floor is going to be x, comma, y, comma, nothing, because it has no height, because it's on the floor. If you think about this one, where we're on the front wall of this room, what don't we have? What's our 0 on that? We don't come forward and we don't go back, right? We're staying on that wall. So any point that's on the YZ plane, it's not going to come out or back, but it can go to the side, it can go up and down. Any point that's on the YZ plane will have an X value of 0. And then the YZ plane, that's the brick wall over on the left side. The only thing there is that you can't go into my room, you can't go out into the hallway, you want to stay on that wall. That means you're just going to keep your Y value 0, because then you're not going to the left or to the right, you're staying right on that wall. I think that's enough for today. So that's the basics of 3D graphing.